Right. Jump was a direct jump, and we had to specify the address, and we have to jump to that address. Now, as I already mentioned, the jump instruction is a long instruction, so it takes 4 bytes, and it's around 3 cycles. Now, if you are desperate about the ROM memory, so that means we don't have enough program memory, that we have limited, we can use a relative jump. Now, relative jump is a 2 byte, which is 16-bit instruction, and the first 4 bits only, 1100, are the opcode, and the rest 12 bits is the relative address of the target location. And this relative address is in the range of 0000 to FFFF. Okay, and this address or this range actually can go either forward and backward jumps. Okay, so it's between 248 and plus 247. So this means that the program counter can go forwards and the backwards, and relative address can be positive or negative in the 2's complement form. Now, our jumps are quite similar to the branch instructions, which we are going to see next. But before we go into that, I want to demonstrate how our jump is operated through a set of instructions. Now, the initialization, so we have got constant 15 and 5 initialized in R16 and R17. Program counter is 0. So label name is over here, relative jump is here. That means we have to jump to over here and we have to perform add instruction again. And then we have got another relative jump, which will go backwards. Okay, so we start, the program counter is 0. And when we are executing LDI instruction, program counter points to the next instruction, which is 1. Then we execute LDI instruction, program counter points to 2. Then when we are in 2, the program counter is showing 3. Now what is happening over there? Now the program counter value plus 1 is showing. Okay, so we are executing instruction 2, but the program counter is showing 3. And then where do we need to jump? The operand is 2. So that means plus 2. So the program counter is 2, plus 1 is 3, plus 2 is 5. And that is the place that we need to jump to. So once we got there, 3 plus 2, 5, we jump and we execute the add instruction. So while we are executing the add instruction, the program counter is pointing to instruction 6. And that instruction is also relative jump label name. Now, as we are getting in there, relative jump, which is the program counter again, is showing PC plus 1, which is 6 plus 1, which is 7. And in this case, we have to go 2 stages back. Now that means that has to be minus 2. So 6 plus 1 minus 2 is the operation that we need to perform. So what is minus 2? It's actually given as an operand FFE, which is 1111, 1111, 1110. If you take the 2's complement of that, keep the first 0, keep the first 1, invert the rest. and this is 2. So we are actually doing that for -2. Now, this is going to be plus FFFE. So we do addition because of the complement, and it points to the 5, and program counter returns to 5, and we go back to add instruction, and we repeat the add operation. So this is how we perform a relative jump using set of instructions. Either we can go forward or backwards based on the relative jump instruction call. Now, another jump instruction that you might come across with is the implicit jump or indirect jump. Now, indirect jumps, they are also 2-byte instructions. Now, when the instruction executed, the program counter is loaded with the contents of the Z register. So Z register can have some values over there, which is acting like a operand to an address in the program counter. So it's like a pointer. Okay, so using indirect jump, we can actually use that pointer value and we can jump to that address. Now, the formation of it looks like it's from 21 to 16. These are all zeros. Okay, and then we have got 15 down to 0, which is the program counter. Now, the Z register is somewhere here, 15 down to 0, and it's pointing for the program counter where it needs to be. Okay, so no operand, it's just a 16-bit opcode. The jump spans between 64K words or 128K program memory. And if the program memory is larger, which it can go up to 8 megabytes, then up to first 6 bits are zeros. So that's what we are doing over here. And that's how we can use indirect jump. So for example, if the register content is 100, the CPU will have to jump to location 100 by executing iJump. Right, so next thing that we are going to talk about now, relative jumps and the branches are similar, as I already mentioned. Now, it's a conditional branch, which are like a branch equal, branch not equal. So based on some conditions, we have to jump to somewhere else. Okay, and we call them actually short conditional jumps, and we are calling them short branches. Now, how are we going to do that calculation, and how do we do that? That's what we need to talk about now. Now, branch instructions, so BRXX, it can be equal, less than, or greater than, and not equal, and they are just 2-byte instructions, which is 16 bits again. And opcodes are generally 9 bits, and the relative address is 7 bits. So the target address is relative to the value of the program counter. And if the relative address is positive, the jump is forward. And if the relative address is negative, then the jump is backwards. So like we were doing in the R jump, we can actually go forward and backward with the branches as well. So this means that the relative address is in the range of -64 to +63. And in order to calculate the target address, the relative address is added to the PC of the next instruction. So this means that the target address is equals relative address plus the program counter. Now, I can easily design this to show how it operates. 15 down to 0 is our program counter. Then we do an addition. So +1. This will be fed. And the instruction is opcode and K. So this K is actually the range or the address, let's say. 15 down to 10, 9 down to 3, and 2 down to 0. And this is how we perform the branch instruction. So branches, if the condition is true, again, we do program counter is program counter +1 plus the operand. Otherwise, it will just do program counter +1. Now, we can actually do these branches, and we can easily calculate how many times we are going to jump forwards or backwards, how many steps. These are all can be calculated from the opcodes given. So now the branch instruction list is given over here, and they are just conditional jumps, branch equal, branch not equal, and which flags are set in the status register are all given. You don't need to memorize them, but you have to know how to use them. So we have to specify where to jump, less than, half carry, T flag, branch minus, and so on. These are all can be found. And the sign flag in AVR, which is negative XOR overflow, is true sign of a comparison. So how are we going to use these conditional jumps is what we are going to see next. So conditional jumps can be used either for the conditions or for the loops. So condition, for example, when B is subtracted from A, if the result is 0, that means A is equals B. And if there's a carry set, that means A is greater than B. This is a typical condition. Now we have got a couple of exercises. Let's go over together. Write a program that compares R20 with R21. If R20 is equal to R21, then R22 increases. So in order to check if they're equal, we can subtract and we can check the 0 flag. So what I can do is subtract instruction R20, R21. And if branch not equal, that means if they are equal, Z flag will be set. If not equal, jump to next. So let's say next, and next is somewhere here in the program. And otherwise, if it's not branching, it has to increment R22. Okay, so when we compare it, the Z will be set if they're equal, and Z will be not set if they're not equal. Now, the subtract instruction is going to change the value of R20 because it's like R20 minus R21. Okay, so it's actually updating that. If you want, you can also use compare instruction if you don't want this value to be changed. So compare R20, R21. It's the same operation. The second one, it says write a program that compares R26 with R24, and if R26 is less than R24, then R22 increases. Okay, so we have to check if R26 is greater than R24. That means we have to do a SAP R26, R24. And in this one, we can check if carry is set or cleared. So I'll do BRCC and jump to label 1. Now, when we are doing BRCC, if carry is cleared, this is carry cleared, we have to jump. If carry is set, then we have to increment R22 because that's what it's saying. Set means that means R26 is higher. So the carry flag is set, then I have to increase R22. These are simple conditions that you can develop further, and you can have more complex conditions. But branches are lifesavers, and they are easy to use, and we can easily jump forwards and backwards in the program. Example 3. Write a program that compares R26 with R24. R26 is greater than or equal to R24. So again, we subtract, we check if the carry is set rather than cleared, and we increment R22. Okay, so if R26 is greater, then the carry will be set and we do nothing. Otherwise, it will increment. So if-else statements, write an AVR assembly for the following. R17 is 5. So if R20 is greater than R21, increase R22, otherwise decrease R22, and then increase R17. Okay, and the flow chart is also given. So we had to define the value for R17. LDI R17 is 5. And then we have to check if R20 is greater than R21. Subtract R21, R20. And based on the subtract, if the carry flag is set, branch carry set, L1, then we have to jump to L1. And what we need to do, if it is greater, then increment R22, and then increment R17. If we are not satisfying that condition, we have to decrement R22 and we have to jump to next, because in both cases R17 has to be executed. So I'll say next for this one. Okay, so either from the branch we go over here and we execute these, or we go through this and we execute that. Another one is a loop. Write a program that executes the instruction at R30, R31 9 times. Now, how can we create a loop using branch instructions? We have done a similar example before. We can say that we have to repeat it 9 times. I will set a counter LDI R16 9, so that will repeat 9 times. Then what I do is I perform add operation at 30 and R31. Then after the addition, I have to decrement the counter R16, and I have to check if it is 0. The counter is 0, so branch not equal R16. Now, if Z is equal 0, then branch and go back to, sorry, branch, not R16, branch to label L1. So this is actually going to check if R16 is 0 or not. If it's not 0, go back to add a operation and carry on until we are done. If it is 0, then L2, which is R jump L2. We just wait there forever. Another one, write a program that calculates the result of 9 plus 8 plus 7 plus, it goes down to 1. So we are just decrementing the value of the register and we are adding it again. Now, again, this is going to be like 9 times. So LDI R16, it's going to be 9. Then LDI R17, where we are going to do the operation, we initialize that 0. So we perform the add operation, R17, and I can just put 9 over there, R18. So this is going to be like 9 plus 0 at the beginning, or 0 plus 9. Let's do it in the way that registers are. So we have got 9 in R17. Then we decrement the counter. Okay, now that becomes 9 minus 1, 8. And then this is in R16. Then we check if it is equal 0 or not. If it is not 0, go back and add the next value that we have put it in R16. Otherwise, we have to do a jump and wait there forever. Okay, so when the count is 0, we get out of the loop and we wait there forever. So loops, you can use for loops, the initialization, the condition, and the calculation, and then what you need to do when you satisfy the condition. Yet another example, write a program that calculates 1 plus 3 plus 5 plus, and it goes up to 27. So we are actually counting or adding the odd numbers. Let's start with LDI R20. which is 0, and LDI R21, which is 1. Then I do an add operation because I have to have R20 as a value of 1. Then we have to define another variable, let's say R22, and that will be 2. And then add R20, R21, and R22. So I want to write a few comments. R20 is 0, R21 is 1, then R20 is 0 plus 1, which is 1, and R22 is 2, and then R21, it's going to be 1 plus 2, which is 3. And then we have to define where we need to stop. So LDI R17, let's say it's 27. We have to stop at 27. So the counter is for 27 and subtract R17, where we have got the number is R21. So we have to put R21 over there. So 27 minus 3. Okay, and then we check if the carry cleared, then jump L1. Where is L1? We go back to add operation. So this is how we do looping and conditional statements using branches. Now, another interesting function call or instruction is call instruction. Now, call instruction is actually used to call a subroutine, or you want to call a function, you just use call something. Now, subroutines are often used to perform the tasks which they are need to be performed frequently. And we are using subroutines to make it more structured programs, and we are actually using them to save some code space. So call instruction is another large instruction, which is 4 bytes. So it's 4 bytes, 32 bits. And the 10 bits of it used for opcode, and the other 22 bits, which is K21 to K0, are used for the address of the target subroutine. So it's similar to jump, but you're actually specifying where is your subroutine is. So you have to write that address. So as we are having a 22 bits as an address range, like a jump instruction, that means we can jump to 4 millions of address space. So 000 to 3, F, 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 F. Now, when we are doing this operation, the call instruction, let's say, imagine that you are running an ordinary program and you suddenly see a call instruction that you have to jump somewhere else in the program counter. Now, how does the CPU understands when it confirms or completes that function or the subroutine, it has to return back. So when it returns back, how does the CPU knows where to return back and which instruction needs to execute next? Now, what the microcontroller is doing when the call instruction is executed, the microcontroller automatically saves the value of the program counter onto a stack where it actually shows or stores the next program counter value after the call instruction. So this is saved in the stack, and then when the subroutine is completed, the microcontroller gets the value from the stack, puts it back into the program counter, and goes back to where it is directing it to. So what is stack? Now, stack is like a container. So it's like a FIFO, first in, it's not FIFO, it's first in, last out. And so it's starting from the bottom and you're filling up the container. So if you want to use stack, you can actually use push and pop instructions. If you want to push something into this stack, store it apart from the call instruction, you can use push and you can use pop. So push the value of the GPR, and then the stack pointer moves up one, and the pop is just when you want to retrieve back the value from the stack, we use the pop instruction. So stack is a 16-bit stack pointer, which points to the value in the memory. It's a 16-bit address. So it is actually placed inside of a RAM where we have got the stack over there, and the address or the stack pointer is pointing with 8-bit value, a 16-bit value, which we have got two registers which are holding that address pointer values, SPH and SPL, stack pointer. Now, if you want to define stack, we can say that it is the section of RAM used by CPU in order to store information temporarily as we are using RAM. You can find the stack pointer SPH and SPL in the IO memory space, which are two registers over there. Now, in the stack, you can actually store information which could be a data or it could be an address. And CPU is actually needing this stack space as they have got a limited number of registers. So in order to access the stack, the register inside of the CPU, stack pointer, SPH and SPL is used, and we can point to the stack and we can write or retrieve the value we require. So let's see how we can demonstrate the stack. So we have to first initialize the stack. RAM end, which is given in the definition file, is the end of the RAM memory, which is hex 10FF. This is always the case for 128 AVR. So what we do is higher element is getting the higher byte, and lower element is getting the lower byte address of that RAM. Okay, so these are actually initialized. So if we go through, LDI instruction is executed, then out SPH, that means 10 is the address high. So we know that stack pointer 1000, and then we can set the low part of it, which is FF, and that will be placed into the SPL. So that means this is becoming the end of the RAM memory. So stack pointer is now showing 10FF. Okay, so we initialize the RAM. Then LDI R20 hex 10. So R20 will have the value 10, and R21 will have the value 20, and R22 will have the value 30. So R20, R21, R30, as they are initialized with LDI, they place into these registers. Now, push means we have to store the value of the register into the stack. So R20 is 10, so that will be stored in 10FF. So that will be over here, and stack pointer is moving, decreasing the pointer value and showing the 10FE. Now, at this point, it's 10FE, and we are pushing R21, which is 20. So we have got 20 over there. And this one is also decremented again. And we have to push R22, which is 30, into this stack, and that's also decremented. Now, after the push, there's a pop. That means we have to increase the stack pointer to the next one, and that will be stored in R21. So over here, so the first value is 30, so 30 will be stored in R21. Then a pop R0, so 20 will be stored in R0, and pop R20, that means 10 will be stored in R20. So as you can see, we can easily access to the stack, and we can write the data to it by using push command. So if you have any questions, please note them down. When we have a live lecture, feel free to ask. Now, we have demonstrated the stack with the push and pop. We can also demonstrate the stack with the call function, as I already mentioned. So call function, once again, is a 4-byte of instruction, and we can span it to 0000 to 3FFFF, 4 million addresses. And let's see how the call function is working in an instruction with the stack. Again, we initialize the stack. We have got LDI R20 15, LDI R21 is 5, so we have got two constants. Then we have the function call. So as you can see, when we are in 5, the program counter is going to show next 6. So when we are in address 6, now as it is calling a function and the function name is in 0A, I have to jump 1, 2, 3 steps. 1, 2, 3. But as the program counter increments the value of it, you don't need to take care of that, because in the call function and in the jump functions, you just specify the address and you jump there. So it's specified 0A, then it has to jump to 0A. Now, while it is jumping to 0A, this is important, the next address is 08. So program counter is incremented, is 08. So this 08, before it gets into 0A, it has to be stored in the stack. So when the call function is used and the next program counter address is loaded into stack. Now it is showing 0A as it needs to jump. It performs the addition, it performs the subtraction. Again, it's pointing to the next address, and this is return. Return means returning from the subroutine. That means it tells the CPU to, okay, get your program counter address that you have got before the function call. So I can start from there. So it retrieves the stack value while it is in the red. Okay. Program counter again it's incremented. So 0008 is there. So that means as this is going to be the program counter, we have to go back to 08. So the program counter shows and we jump back there to instruction 8, which is increment R20, and wait there forever in L1. So this is how we operate the function and the stack with the function call. Now, when we have mentioned the loops, and when we talked about how these loops can be used in order to generate some wait operations, or maybe we can use loops to generate time delays, which is all possible with the AVR. Now, how we call the time delays and how we can generate those time delays are also important. So next thing that we are going to see is the delay calculation for AVR. Now, the CPU cycle time is determined by the internal CPU clock. And Atmega 28 has many clock source options, which we are going to see them later on. And internal oscillator can provide up to 8 megahertz CPU clock, and external mode can provide up to 16 megahertz of clock. Now, in order to create a delay, we have to first know the CPU clock and the period. So in order to create a time delay using assembly instructions, so we have to know two things in order to make the accurate calculations. The crystal frequency, so the frequency of the oscillator connected, and we have to know the AVR design, and we have to understand how microprocessor instructions are working. So AVR is working with the RISC architecture, as we have mentioned in the first lecture, and they have got a fixed size instructions, and it's also using pipelining, so fetching and executions are overlapping, and we can easily use those in order to make the accurate calculations. So typical time delay can be calculated as LDI instructions are all one machine cycle. You can find these details in the data sheet. So LDI is 1 clock, move is 1 clock, add is 1 clock. So for each of those, we have 1 clocks, and that will give us total of 5. Then we know the CPU clock is 10 megahertz. That means 1 over 10 is 100 nanoseconds is the period. So we have got 5 machine cycles by 100 nanoseconds. That will give us 500 nanoseconds delay. So another one, the branch is also included over here. Now, LDI instructions are one cycle, add is one cycle, decrement is one cycle. Now, when we are talking about branches, it shows 1/2. Now, where is that 1/2 is coming? Branches are conditional. So if it is true, you execute something. If it is false, you execute something. Okay? Now, if it is true, if you are satisfying the condition, then you go to the next instruction, where the program counter is pointing to. But if, let's say, if your program counter is showing the next instruction, but you have to return back and repeat it, that becomes the branch penalty, because your program counter is already incremented, but you have to jump back. So how do we do the calculation for it? Now, over here, as you can see, we do LDI, add, decrement. So maybe I can rewrite that. LDI R1600, add R17, R16, decrement R16, and branch not equal again. So again is over here. Okay, now this is one, this is one, this is one, branch is 1/2. Now how do we do the calculations? First of all, this is going to be repeated. How many times? It has going to be repeated 100 times. Okay, so that means this is going to be 100 times, this is going to be 100 times, and this is going to be 100 times. So we can say that we have got 100, and we know that 1 plus 1 plus 2. Okay, so program counter incremented, and then we jump to somewhere else. This is actually 2 cycles. Okay, if this is true, it's 2 cycle. Then if it is false, it's just 1 cycle, which I need to add that over there as well. So in order to calculate the delay, we have got 100. This is 4 minus 1. So it's going to be 400 minus 1 is 399. Okay, so this part is 399. And I also need to add this LDI instruction plus 1. It's going to be 400. Now, number of cycles are 400 because we are creating or repeating it 100 times. Then if the period is 100 nanoseconds, that means the delay is going to be 400 times 100 nanoseconds, which is 40 microseconds. And this will be the delay of that complete instructions given over here. Another example which is given. So LDI R1650, no operation. NOP is no operation, it's just a single cycle delay. Decrement R16 and BRNE L1. So I'm just going to put L1 rather than again. Once again, the clock cycles 1, 1, 1, 1, and 1 over 2, as we have got branches. Now, the inside of this, as we have 50 times that we need to perform it, this is going to be repeated 50 times. So it's actually going to be times 50, times 50, times 50, and times 50. Now, the number of cycles, so 50, 1, 2, 3, 1 plus 1 plus 1, plus when it is true, minus when it is false. So 50 times 5 minus 1. So 250 minus 1, 249. So that's number of cycles. And if we are using period as 100 nanoseconds again for 10 megahertz, this is going to be, and we also need to add this one, which is another plus 1, 250. So that means the delay is 100 times 250, which is going to be 25 microseconds. And that will be the result of that delay. So considering a user register cannot be loaded with a number greater than 255, can we obtain larger delays? We can actually obtain larger delays by creating nested loops. So let's see that example. LDI R17 is 20. LDI R16 is 50. NOP, NOP, decrement R16, branch not equals, return back to L2, and then decrement R17. This is just a random code that we can generate loop inside of a loop, BRNE, L1, and that L1 is over here. Now, from the data sheets, we can easily get the number of cycles for each of these instructions, 1 and 1 over 2. Now, what is happening is this one this one is repeated 50 times, and this one is repeated 20 times. Okay, now 50, 50, 50, 50, and also 20, 20, 20, 20, 20, and of course this one is 20, and this one is 20. Now, let's start with the 50 part. So 1, 50 times 1 plus 1 plus 1 plus 2, and minus 1 when it is false. So 50 times 5 minus 1, so it's going to be 249. Then I can include that with A20, where I have got 20 times 1 plus, this is included, 1 plus 249 plus 1, and branch plus 2 and minus 1. So 20 times 249, 250, 251, 253, minus 1. So this is going to give us 5060 minus 1, 5059. And then we also have one other LDI plus 1. It's going to be 560. And then, of course, we can use 100 nanoseconds, and we can multiply by that, which we are going to get 506 microseconds. So this becomes the end of this chapter, which we have talked about arithmetic logic instructions, branches, calls, and time delay loops. Thank you.